For nearly 100 years, it has been hiding in plain sight. It has no color. It emits no light, undetectable by any instrument humanity has ever built. And yet, without it, every galaxy in the universe would tear itself apart. Without it, no star system would hold together long enough for a single planet to form. Without it, you would not exist. It is called dark matter. It makes up 85% of all the mass in the universe, and in 2026, for the first time in nearly a century of searching, scientists are no longer saying, we think it's there. They are saying, oh, we may have finally seen it. This is the story of the most important scientific breakthrough in a generation. And it is happening right now from multiple directions simultaneously in ways that are reshaping everything physicists thought they understood about the invisible architecture of the cosmos. Now let's start with what dark matter actually is, because the name is deeply misleading. Dark matter is not dark in the way a dark room is dark. It is not just matter that happens to be in the shadows. It is matter that does not interact with light at all. Ordinary matter, everything you can see, touch, or measure, is made of atoms. Atoms interact with photons, the particles of light. They absorb light, they reflect light, they emit light. That is how we see anything. Dark matter does none of that. It does not absorb a single photon. It does not reflect one. It does not emit one. It is completely and utterly transparent to the entire electromagnetic spectrum. Radio waves, visible light, X-rays, gamma rays, all of it. The only force dark matter appears to respond to is gravity. And that gravity, its sheer, invisible, massive gravitational pull, is the only reason we know it exists. The evidence for dark matter is overwhelming and has been building for decades. In the 1970s, astronomer Vera Rubin made one of the most important observations in the history of cosmology. She measured how fast stars rotate around the centers of galaxies. According to Newtonian gravity, stars at the outer edges of a galaxy should orbit much more slowly than stars near the center. The same way the outer planets of our solar system orbit the sun more slowly than the inner ones. But Rubin found something completely different. Outer stars were rotating at almost exactly the same speed as inner stars. The rotation curves of galaxies were flat, perfectly, stubbornly, inexplicably flat. The only way to explain that was if there was an enormous invisible mass, a halo of unseen matter surrounding and permeating every galaxy, providing extra gravitational force that prevented the outer stars from flying away. That halo is dark matter. And Rubin's observation was confirmed again and again by every subsequent study of galactic rotation. The cosmic microwave background, the ancient afterglow of the early universe, also carries dark matter's fingerprint. The precise pattern of temperature fluctuations in the CMB tells cosmologists how much ordinary matter and how much dark matter existed in the early universe. The answer is consistent every time it is measured. Approximately 5% ordinary matter, 27% dark matter, and 68% dark energy. Dark matter is not a minor correction to the standard picture. It is the dominant form of matter in the universe, outweighing all visible matter by more than 5 to 1. It is the skeleton on which the entire cosmic web of galaxies and galaxy clusters is built. And yet for nearly a century, every experiment designed to directly detect it has come back empty. This is the paradox that has haunted physics for decades. Dark matter must exist. The gravitational evidence is beyond dispute. But what is it made of? The leading candidate for most of the past 4 decades has been the WIMP, the weakly interacting massive particle. WIMPs are theoretical particles heavier than protons that interact with ordinary matter only through the weak nuclear force and gravity. They were elegant. They solved the dark matter problem naturally from extensions of the standard model of particle physics. And they were testable. Because if 2 WIMPs collide and annihilate each other, they should produce a burst of high-energy gamma rays. Detect the gamma rays, find the WIMPs. The problem is that every experiment built to find WIMPs has failed. Underground detectors in mines on multiple continents, shielded. From cosmic rays, cooled to fractions of a degree above absolute zero, built with the most exquisitely sensitive instruments ever created, have been searching for decades. The large underground xenon experiment, the Xenon 1T experiment, Pandex in China, Lux Zeppelin in South Dakota, every one of them has come back with the same result, nothing. The Lux Zeppelin detector, which reached a significant milestone in 2025 and 2026 as the most sensitive dark matter detector ever built, has set the tightest constraints ever placed on WIMP interactions. Its sensitivity is so extraordinary that it can detect an interaction that might occur once every several years in a tank of liquid xenon the size of a car, and it still found nothing. The absence of a WIMP signal in Lux Zeppelin is not a failure of the experiment. It is a result. It is telling us that if WIMPs exist, they interact far more weakly than any model predicted, or they do not exist at all. This is the crisis that has been building quietly in particle physics and cosmology. Dark matter is real. WIMPs are not showing up anywhere. And into that crisis, in late 2025 and early 2026, the first and most dramatic came on November 29th, 2025. Professor Tomonori Totani of the University of Tokyo published findings in the Journal of Cosmology and Astroparticle Physics that sent shockwaves through the astrophysics community. Using new data from NASA's Fermi Gamma Ray Space Telescope, Totani detected a halo of high-energy gamma rays surrounding the center of the Milky Way. Not just any gamma rays at precisely 20 gigaelectronvolts. 20 billion. In Totani's own words, if this is correct, to the extent of my knowledge, it would mark the first time humanity has seen dark matter. Totani was careful to note that independent confirmation is essential, but he was also direct about what he believes he found. The gamma ray pattern cannot be easily matched to any other known astrophysical source. Pulsars, supernova remnants, or any other conventional process that might produce gamma rays at that specific energy and in that specific spatial distribution. By a process of elimination as thorough as any he could construct, Totani concluded that what Fermi detected is the annihilation signature of WIMP dark matter at the galactic center. If he is right, but Totani's WIMP detection is only one piece of the 2026 picture. Because at the same time that the University of Tokyo was publishing gamma ray evidence for particle dark matter, a completely separate team of researchers was publishing evidence that dark matter might be something entirely different. In January 2026, a team led by researchers from Johns Hopkins published a study in the Journal of Cosmology and Astroparticle Physics, proposing that dark matter might not be a single particle at all. It might be two particles, two distinct species of dark matter that must collide with each other to produce any detectable signal. The research was triggered by a long-standing puzzle. Why does the gamma ray glow at the center of the Milky Way, not in smaller dwarf galaxies, where dark matter density should also be high enough to produce it? If dark matter is a single particle, the signal should appear wherever dark matter is dense enough. That it appears only in certain environments suggests something more complicated is happening. The Johns Hopkins model proposes that dark matter comprises two types of particles whose relative ratio varies from galaxy to galaxy. In large galaxies like the Milky Way, where the ratio is favorable, the two types collide frequently enough to produce detectable gamma rays. In smaller dwarf galaxies, where the ratio is different, the collision rate is too low to generate a visible signal. This would explain why decades of dwarf galaxy searches for dark matter annihilation came back empty. The signal was not missing because dark matter was absent. It was missing because the conditions needed to produce the signal were not met. If this model is correct, it means dark matter has an internal structure, a dark sector, far more complex than any single particle theory ever imagined. Then came the fuzzy dark matter discovery. In January 2026, a team of researchers published on ARCIF a gravitational lensing study of 11 galaxies, specifically systems where light bends in sharp, distinctive ways around massive objects. They analyzed what kind of dark matter distribution best explained the lensing patterns. The results were striking. The standard cold dark matter model, the model that has been the backbone of cosmology for 30 years, was decisively ruled out by the data. Instead, the observations strongly preferred what physicists call fuzzy dark matter. Fuzzy dark matter is not made of particles in any conventional sense. It is an ultralight quantum field, dark matter that behaves as a quantum wave rather than as individual discrete particles. Its quantum nature gives it a characteristic wavelength on the scale of thousands of light years, which smooths out the small-scale structures that standard cold dark matter models predict, but that observations consistently fail to find. If fuzzy dark matter is the answer, the universe's invisible backbone is not made of particles at all. It is made of a quantum field, a wave of invisible mass permeating the cosmos, fluctuating and interfering with itself across distances larger than entire galaxies. And on January the 2nd, 2026, Nature Astronomy published a study by an international team led by Sebastian Trojanowski at the National Center for Nuclear Research in Poland, finding evidence that dark matter and neutrinos, the ghostly subatomic particles that pass through ordinary matter almost without interaction, may actually collide with each other and transfer momentum. This interaction between dark matter and ghost particles had never been observed before. The evidence comes from a tension in cosmological data known as the S8 tension. The standard cosmological model predicts that the universe should be more clumped, more concentrated into dense regions like galaxies and galaxy clusters. Then observations actually show the universe is smoother than it should be. Trojanowski's team found that if dark matter and neutrinos interact, that interaction would transfer energy away from dense regions, smoothing things out, and the smoothing matches the observation precisely. The study found a signal at 3.5 sigma, not yet at the 5 sigma gold standard required for a confirmed discovery, but strong enough that Trojanowski called it potentially a fundamental breakthrough in cosmology and particle physics. Meanwhile, deep underground in a nickel mine near Sudbury, Ontario, a detector is coming online that may resolve all of these competing theories at once. The Super Cryogenic Dark Matter Search, Super CDMS, reached its target operational temperature in April 2026. The detector sits in Snow Lab, one of the most shielded underground laboratories on the planet, at a temperature nearly 1,000 times colder than outer space. It uses semiconductor crystals embedded with cryogenic quantum sensors designed and built by Dr. Rupak Mahapatra and his team at Texas A&M University. Super CDMS is targeting light dark matter, a much lower mass form of dark matter than WIMPs, at energy scales that previous experiments were completely blind to. If dark matter, particles exist in the mass range. Super CDMS is searching. The experiment will either find them in its year-long science run, or it will set limits so tight that this entire class of dark matter candidate can be definitively ruled out. Either result reshapes physics. The picture that is emerging from all of this research simultaneously is one of the most extraordinary moments in the history of science. 5 completely separate research groups using 5 completely different methods, gamma-ray telescopes, gravitational lensing, neutrino interaction data, quantum field theory, and cryogenic particle detectors, are all converging on the same conclusion. Dark matter is real. We are finally beginning to see it, and it is almost certainly more complex, more strange, and more interesting than any single theory predicted. What this means for our understanding of the universe cannot be overstated. Dark matter is not a peripheral mystery. It is the central mystery. It is the substance that made the formation of galaxies possible. It is the scaffolding on which every visible structure in the cosmos is built. Without understanding it, we have only understood 5% of everything that exists. With it, we finally begin to understand the universe as it actually is. Not the thin sliver of visible matter that we can see, but the vast, invisible dominant majority that has always been there, shaping everything, controlling everything, invisible to everything except gravity, and now, finally, to us. Professor Totani's gamma-ray finding, if confirmed, will be the most important astronomical discovery since the detection of gravitational waves in 2015. The fuzzy dark matter finding, if confirmed, will fundamentally rewrite particle physics. The neutrino dark matter interaction, if confirmed, will solve one of the most persistent tensions in modern cosmology. And Super CDMS, in its year-long run that has just begun in April 2026, may deliver the definitive answer. Not evidence, not hints, not statistical anomalies, but a direct, unambiguous detection of dark matter. Particles interacting with ordinary matter in a controlled laboratory environment. For nearly a century, dark matter has been the ghost haunting the universe, the invisible force that shapes everything and reveals nothing. The 85% of existence that we knew was there but could never touch, measure, or see. That era is ending. The detectors are cold, the telescopes are watching, the data is coming in. And the biggest mystery in the universe, the question of what the cosmos is actually made of, is finally beginning to yield its answer.